Our last talk for this afternoon is M.Ballard, and he's going to tell us about exceptional collections and rationality.
Well, thank you, Tony, for the introduction. I'd like to thank the organizers for the invitation. It's always a pleasure to speak here. I've got a tough act to follow, but hopefully it'll be something you can get out of this. If you get bored and you're mirror symmetrists, here's an exercise to think about for the next 60 or so minutes. So give me the mirror to this, oops, curve. Okay. The only little bit of difference, bit of a difference, but is that. Okay. Anyway, you get bored. So what I'm going to talk today is joint work with Alex Duncan, who's at South Carolina, Alicia Marsh, who's my student who's fishing. She'll be somewhere next year, and Patrick McFadden, who is at Fordham. We still have that eye on the board, so I guess that's a good way to occupy people's time. And the basic question is the following. A metaphysical question, because it's not completely precise, but if you take a field, just a general field, take a smooth projective variety over it, and you look at the derived category, what can you pull out of it to tell you about the rationality or non-rationality? Okay. And the general expectation, and you can see from what we saw in Maxime's talk, semi-orthogonal decompositions, or the structure of the set of semi-orthogonal decompositions, should have a strong influence on the rationality, or at least the non-rationality of the variety. So we heard a little bit about a related thing just a moment ago, but I'll just remind you of Kuznetsov's conjecture for rationality, that if you had a semi-orthogonal decomposition with this component, it was equivalent to the derived category of a commutative K3 surface if and only if the cubic fourfold was rational. So that's sort of a flagpole you can put up and give an example to illustrate the previous principle. I'm not going to talk about that. What I'm going to talk about is, like anything, trying to take it to its limiting situation where you can try and learn something to start with and then build back up, hopefully. Okay? So, if the structure, some amount of rationality or non-rationality is encoded in the set of semi-orthogonal decompositions, then one of the first things I should look at is the implications of the simplest semi-orthogonal decompositions on the rationality of the variety. Okay, what are the simplest ones? Well, the simplest ones are exceptional collections. When your derived category or your category is built out of derived categories of points. And now I'm going to work over a general field because it gives me a lot more interesting examples to play with, particular questions to answer that aren't, as you'll see, sort of gobsmackingly obvious over C. So here, what do I mean for an exceptional collection? An exceptional object. I'm going to start with just division algebra. And related to the exercise there, you can take the base field to be R and take the unique non-trivial division algebra, the quaternions over it. An example. And then an object is exceptional, well, if it has no non-zero degree x between itself. And that's endomorphisms of just this fixed division algebra. Okay. And we label it with an A. I'm going to take the convention that if I say exceptional, it'll mean for some division algebra. Maybe that's not the best one. But when I say so of course if we go to an algebraically closed field or a separably closed field, this notion degenerates into the usual one. We just have k exceptional. But in between, we could have maybe not a non-commutative thing, but just a finite separable field extension. Something that's a little bit more mild in terms of the endomorphisms. Like say, I don't know, C over R. So if the exceptional objects endomorphisms are just a finite separable extension, I'll call it a tall exception. So a tall exceptional is the correct statement about your derived category or whatever category built out of derived categories of points, smooth points, over non-closed fields. Yeah. Okay, so make the first obvious pass. Say that X possesses a full exceptional collection. Is it rational for the field? Okay. You have to remember what my definition of exceptional is in order to clarify this. But as a first pass at a question, it's not so bad. If it's k exceptional, meaning the endomorphisms are just the base field itself, no trivial Galois action going around, then Orlov says, yes, in fact it is rational. And even stronger, Valeri conjectures that your variety can be decomposed into pieces. The big piece is rational, pieces you're missing are rational, the pieces you're missing from those are rational, in a way that it's built up by this cut and paste method completely from rational things. So not just the big piece, but every piece of it as you decompose it in some motivic fashion is rational. So he calls that tape. I think that's a good name. Okay. So k exceptional, expectation is yes. Here's an example. Looks familiar from the board over there. So here we have a semi-orthogonal decomposition. In general, for such varieties, this is written down by Bernardara. It's got the structure sheaf, and in this case, we have a rank 2 vector bundle whose endomorphisms are the quaternions. Okay? This is clearly not rational because it has no points over R. Easy way to tell something's not rational. Okay? So this general notion of exceptional, where I include division algebras, definitely not rational. I think my next slide is the table. Yes. Okay? So full exceptional collection. Are we rational over K? K exceptional. We expect yes. A little star up there because it's not a proven statement. A tall exceptional, I have a question mark because I haven't given you evidence either way. I have a little star up there because you can do really silly things like just take spec of a field that's not K. Okay? But if it's, say, geometrically reducible, it becomes a little more interesting question. And then if you're just straight up division algebra, exceptional answers no. And what's the evidence for this? The evidence doesn't go much beyond one slide. So in dimension 1, if we have a smooth projected curve, then you're actually P1 over the field if and only if you have a full tall exceptional collection. In fact, your full tall exceptional collection has to be K exceptional in that case. How do you work something like this? Well, you go up to the separable closure, use results of other structure derived categories over curves. Genus 0 can't have them. Genus higher than 1. Genus 1. Genus 1's the whole, right? Yeah. Genus 1 you can't have them. Genus 2 or greater, you can't have them by result. I think. And then you know automatically it's a Severi-Brauer curve, and you use some non-commutative modes to tell you that Severi-Brauer curves are trivial if and only if they have a full exceptional collection. Okay. Now we go to dimension 2, already things get a little more, no, not as thorough. So Morgan Brown, who's here at Miami, and Ian Shipman, what they showed is, I guess I didn't specify, so this is over C here, the first statement. If you have a full strong exceptional collection of line bundles, then in fact you're rational over C. And Vial, sort of in a complementary direction, that if you already are rational over the separable closure, your geometrical rational, and you have a full exceptional collection, full K exceptional collection, I should put that there because this is now over a general field. then you're in fact rational. And he doesn't even need a full exceptional collection, k-exceptional collection on the nodes. He just needs it basically in the co-amount. He calls it numerical exceptional collection. Automatically tells you you're rational for surfaces. Okay? So those are the situations where we have some class of examples where we can conclude rational, at least for the exceptional collection. Some things that are also not counterexamples, if we take a perfect field and we take a rational surface over a perfect field, then it's known that the derived category always has a full a tall exceptional collection. It's clear you can't get away with a full k exceptional collection because your ranunculus field is local point. That's not k in the projective space. Now you have a tall exceptional collection. Okay. And Manin's classification of rational surfaces, minimal rational surfaces, and work of All and Baradara for Del Pezzo surfaces. You put that together and this comes out. Okay. Also, not counterexamples, all the knowledge we have about what varieties have exceptional collections. Varieties that have exceptional collections are usually quite special. They satisfy this conjecture of valarity. They're built out of affine space, open pieces of affine space. So, in some sense, this should not be that hard of a question, because these are exceptionally special things that we see in day-to-day life as a mathematician, that when they have exceptional collections, have a very rigid structure in terms of their rationality. Okay. So, if I'm going to try and understand this question, what do I want to do? Well, like I said, I want to try and take it to a situation that's decently well understood under some assumptions. And over C, what we have is we have a lot of homogeneous spaces with exceptional collections. So let's make it even better. Let's just say that I have a linear algebraic group over my base field. And when I say linear algebraic group, I mean a smooth, finite type, definitely not a scheme, or a characteristic DP. Okay. And we're going to go from linear algebraic group to torus in a bit here, so don't worry too much about that. And let's say X is a smooth projective compactification of the group G. So we're talking a bit about toric varieties, for instance. Toric variety is such an example. So for these classes of varieties, is this conjecture of Orloff true? If I have a full k exceptional collection, am I automatically rational over the base field? Okay. Now, over C, this is a nonsense question. Or over any separately closed field, this is a nonsense question because these things are automatically rational. Such groups are automatically rational. That's what But it is a meaningful question over non-closed fields. And then, we can ask, so with k exceptional, we saw, at least for surfaces, we had to allow a tall exceptionality. We talked about derived categories of all rational surfaces. So, can we say anything in the Attal set? So if our derived category, all the endomorphisms are finite separable field extensions, could our variety be rational? Could it be stably rational? Does it have to be unirational? Variance on this question. Okay. So, just to give you an idea of what kind of things happen over a non-closed field. So back in '54, Chevrolet wrote a paper that was titled On Algebraic Group Varieties. The goal of the paper was to try to understand when linear algebraic groups are rational, or at least try to compile the existing body of literature and then make a systematic push towards answering that question. So one of the simplest ones that is not rational, in fact, it's not stably rational, comes from the following construction. So let's say I have a field extension, L over K here, and my Galois group is the Klein group. So the simplest non-cyclic group I can have. So here's an example. If you're like over Q, you just take 2 square roots and adjoin them. Okay. Now, so what's this in the middle? The middle here is I take, so I have GM. Is this visible? Let's see. Is that visible at all? Yeah. Okay. People are giving me thumbs up farther back than I expected. Okay, so what do we got? So what is this? This is the Bay restriction of GM from L to K. You should think of this as like L star. Units in L. This is the units in K. I have a norm map between the two, and I can just take the kernel of the norm map. That'll give me a new abelian group, and in fact, a new torus. And what Chevalier showed back in '54, even for slightly more general ones, where I think you took like Z mod P and Z mod P, is that this kernel here of norm map is not a stably rational product. So, reminder, you're stably rational if we can change our reminder from registering, because that has passed. The new reminder is, so you're stably rational if you cross with some number of copies of affine space and you're birational affine space. Okay. In fact, this torus is not stably rational. So, I'm going to reduce from just a general linear algebraic group to just a torus. So what do I mean by a torus? So again, K is my general field. A torus is anything that will base change to GM over the separable closure. And what I had on the previous board, this previous thing here, this guy's called a norm 1 torus. It's the kernel of norm map. Well, except norm 1. So you can check pretty easily that base change this. Of course, you get GM base change this. You get GM to the dimension of the extension, and then the kernel of such a thing is just going to be another copy of GM over the separable closure. Okay. So this is an example of a non-trivial, non-split torus. And its dimension, its rank is just the dimension of the field extension length. And so, what I want to try and understand then is I want to try and understand if I have a smooth projective compactification of such a torus, and it has a full exceptional collection. All the endomorphisms are either copies of the base field or finite separable extensions of the base field. Is the toric variety, is the torus rational? There's one little subtlety about a toric variety in non-enclosed field beyond what I said. Usually over C, you think about it as some type of smooth projective compactification of C star to the R, so that the action of C star to the R extends over the compactification. The only subtlety here is that when I'm over a non-enclosed field, I can, instead of just taking T sitting inside X as an open subset, I can take a torus and then compactify the torus. So really when I say toric variety, I'm talking about a T equivariant compactification of some T torsor over the base field. Coming back to our exercise example here. So if I want to take the norm 1 torus for C stored over R, well, what does the norm map look like? Z times bar Z, real part squared plus imaginary part squared equals 1. Otherwise known as an S1. Pretty much everyone else. And if I look at this Savary-Brouwer curve here, this is an S1 torque variety. And there's no unique way to put a given structure of a torus variety, a torque variety for a fixed torus on such a variety. In fact, you could have different tori for which the same variety is toric under different actions of the torus. So here, this guy here is a S1 torque variety. Here's the torsor, just open piece, that's equal to 1. Right? And the action is what you would expect. Well, this is a e to the I theta here. This is e to the I theta with negative modulus. But you multiply it out in real imaginary components, it still makes sense. And that gives you the action of S1 on this U. And this is a non-trivial torsor because we don't have a point. We don't have a solution to this equation. All right, so I claim this was a meaningful question. So I better tell you that there's at least some non-rational things floating around when I do this, unlike over C. So if you think about what the data come back here, here we go. You think about what this data is algebraically, what are you going to get? Well, over the separable closure, I just have a copy of my usual torus. Functions of my usual torus, Roth polynomials and some number of variables. Okay? And to get back down to T, I'm going to have some Galois action on it. Okay? So really, what I have is, since this splits over some finite extension, I have a finite subgroup of invertible matrices of rank R over the integers. Conjugacy classes of such things classify my tori. Okay. Now, fix your rank, there's only finitely many in a given rank, finitely many in a given dimension. So, given that, you can write it down. It gets progressively more tedious to do this. So things start off simply enough. I have 2 tori of rank 1 possibly over any given field. So this is the total number possible over a given field. This tells me how many of those are rational. This tells me how many of those are stably rational, but not rational. This column tells me how many of those are retract rational, but not stably rational. Another reminder. So retract rational is a notion introduced by Saltman. And if I look at this, it looks like this is a projector of A1, right? So it's a retract, if you prefer that language topologically. But then I could just more generally say that I have 2 rational maps whose composition is equivalent to just the identity on X. That's a weaker notion of rationality than stable rationality. Okay? So things are pretty plain here. Like I said, dimension 1, you've seen the 2 examples over R. Dimension 2, there's 13 possible non-isomorphic tori of rank 2, and all of them are rational. Something happens in dimension 3. There are 73, but 58 are rational. None are stably rational that aren't rational. None are retract rational that aren't rational. Which means if it's always a danger to do arithmetic in front of a crowd. Right? But 15 are not retract rational, as mentioned. And if you remember the dimension of the example I gave for the Klein 4 group as the Galois group, you've seen one such non-retract rational torus. Okay. And then, in principle, you can classify this in any dimension. But as you can see here, it gets larger. So you have 710 possible non-isomorphic tori of dimension 4 over a given field. We have a little asterisk here because we know that there are 7 that are retract rational that are not stably rational. And then what, 200 and some that are straight up not retract rational. But then there are 10 here that we don't know if they're rational or not, but we know they're stably rational. Another fun exercise that's a bit harder for 60 minutes is, does there exist a stably rational but non-retract rational torus? Full stop. Still open question. You like to think toric varieties are about the most basic things in the world. Okay? These tori are always unirational, though. So they give you a nice playground where you can, pick out given levels of behavior rationality by trying to find the appropriate torus. Okay. So as I said before, over a general field with X, some toric variety for a given torus, if its derived category possesses a full exceptional collection, does it have to be rational? Previous table tells you that this is a non-trivial question. You're not going to have anything interesting in dimensions 1 or 2, but maybe in 3 and above. And then maybe we, if we're feeling our oats, we move from the endomorphisms just being the base field to the endomorphisms all being fields, finite separable extensions of the ground field. So, first theorem. So if we take a toric variety and we assume it has a point over the base field, if it possesses a full K exceptional collection, then it is in fact a K rational. Okay. So the answer to Orlov's conjecture is true for maybe toric varieties in the purest sense, where they're compactifications of the torus itself. So remember this point here, the big open is some torsor in general. I got a point, I've killed the torsor, I just have a torus inside. All right, so we were happy we can answer that for toric varieties. We see we know a whole lot about the structure drive categories, we know they're very rational. Over a general field, if we have a full K exceptional collection, we're rational. Now we move to the tall exceptional. Pick your favorite. That's not correct. That should be a 3. As you can see from the previous slide. So for any dimension bigger than or equal to 3, there exists smooth projective geometrically rational varieties. So remember, geometrically rational just means I base change to the separable closure, and I am rational. In particular, an irreducible variety. I don't have things splitting off when I go over K bar. And this is over the rationals. You can do this over a general number field, probably over a general global field, if you have the patience to check some details about things you'll see in a minute. Okay? But The derived category has a full Attell exceptional collection, and it has no rational. So, in particular, what that tells me is it tells me that if I have no points over Q, well, certainly I can't be rational because I have a huge open set of Q points. I can't be stably rational too because I can project off of this guy onto there and get a whole lot of other points over the base field. In fact, I can't be retract rational either. Or even unirational. So
can I ask you a naive question?
yeah.
So can you give some kind of intuition about Orlov's conjecture? Why is originally this fact true anyway? Like endomorphism being the field then you have rational.
Well, I think it originated more over C.
Okay.
Okay.
But
Maybe it's a
what's the
revisionist
big-
history. Larry would know better. But my understanding of how I would go about trying to believe such a statement is as follows. I know a lot of varieties that have exceptional collections. Rachmanians, projective spaces, Borg varieties, other homogeneous spaces. Those also happen to have a very particular structure, motivically. They're all built out of rational pieces. Okay? So, is there some way to convert this data? If I want to make an analogy, it's kind of like these are the critical points of the Morse function, my exceptional collection. I get some cells associated with them. Each of those cells tell me how my variety is rational. It's not exactly that, but that's, wake up in the morning, you're kind of confused. That'd be good. Okay. And then if you have nothing better to do, you have a question over C, you try and figure out if it makes sense over K. Or if you can get anything useful out of it over K. Learn something new that you couldn't learn before. So here we saw K exceptional, torque variety, fine. The example here is also a torque variety. And I'll tell you what it is in a second. But as soon as we go from base field K to finite separable extension, basically all hell breaks loose in terms of the structure of the derived category. There's no guarantee that structure of the derived category will force anything about the rationality of the variety into place. So, some notes on the proof. So this is the proof of the first one. So it's well known how to understand the rationality properties, not necessarily rationality over K, but come back here real quick. This table. These two properties, stable rationality and retract rationality of a torus, you can basically write down a program if you're given a presentation of a torus with a finite subgroup of invertible matrices over the integers to tell you whether or not these conditions hold. You replace it with some particular resolution as a module over the Galois group. If the resulting module is, if it has a basis that's permuted by the Galois group action, if I have a finite group, I have a lattice that acts on that by automorphisms. There's no guarantee that I'm going to have an actual basis that gets moved around under the finite group action. If I do, that thing I make from the torus is stably rational. And then if it's a summand of such, it's retract rational. And there's no, unfortunately, simple characterization of rationality. Okay? So I mentioned that you do something to the torus itself, some resolution of it. In fact, the resolution is, the resolution is what everyone does in torus geometry every day of their life. So, over the separable closure, it's just a copy of GM. I have the torus. I have a map to divisors, which maps to line bundles. And this thing here is actually a representative of the invariant you extract to understand the rationality of the torus. This thing here with it's Galois group action. So if you have a basis of line bundles permuted by the Galois group, then your torus is in fact stably rational. If you have a basis of line bundles, well, if this is a summand of something, where you have a basis of line bundles that's permuted by the Galois group, this torus is in fact retract rational. And that's a nice characterization, because most of the conditions you have when you try and extract invariant about rationality tells you, if you're rational, this must be true, and then you argue backwards saying this condition doesn't hold, so therefore you're not rational. Whereas, at least for tori, you have it boiled down into some simpler linear algebra S condition. Okay? So, and when you think about what K-exceptional is, K-exceptional means I have almost no useful, no interesting Galois structure up here whatsoever, and anything I can build out of the cohomology of my variety. Because my cohomology is built out of copies of K as an exceptional collection. K has no Galois action. So anything built from it should have no Galois action. In particular, I look at this K naught. It surjects onto this Picard group by the determinant. Well, this has trivial action, this has trivial action. And in fact, I said there was no condition in general. This is not equivalent to rationality, but if you know that the Picard group carries trivial Galois action, then in fact, this is an old result of Boston-Brzezinski. Did I say that right? I always get correct. You can check it's rational. Right. So that's the first one.
So that's also in an algebraic closed as well.
Huh? This is this.
No, the rationality implied by Picard group having a trivial action. Does it hold over K as well?
This is all. I mean, I can't talk about Galois action unless I go up to K bar. But this is a statement about.
Sure.
Any questions?
This holds only for coding part.
Yeah, this is language one. So you can ask about taking your favorite linear algebraic group. Everyone's favorite to do kind of arithmetic is E8. So if you have a homogeneous space for such a thing, or a smooth predictive classification, you can ask similar questions. That I don't know the answers to.
And so one more time, is retract rational or stably rational? How is it? What's the property on the exceptional collection?
It's not an exceptional collection. It's just on the card group. Say K bar is C. Right? So the algebraic closure is just C. Right? So what you have is you have something defined over. I'm gonna say that Q bar is C for, but that's stupid. Let's say you have something whose algebraic closure is C. It's K. K is the field. Okay, you have something defined over K. You base change it to C. Now you just have your usual torque variety. Right? You have your torus invariant. You have your torus invariant divisors. Keep my notation consistent. And then you have your classes of the card group. Okay. Now, this thing carries a Galois action because, if I have a line bundle, I pull back by the Galois group, I'm getting another line. What is the structure? And this is this is Z to some rank R. Maybe rho is better since it's. And this factors through some. This action factors through some finite group, basically. So what do I have? I have a finite group acting on a lattice. If that lattice has a basis that's permuted by the finite group, then X itself is stably rational over K. If and only if. Well, a little bit care has to be taken, but basically. And then if it's a summand of such a thing, a summand of a permutation module, or you add a permutation module, it's a summand. I'm getting a little sloppy here, so people watching online, please forgive me. Then it's retract rational. Okay. But it's nice. It purely captures the two invariants in terms of simple linear algebra over C. All right. So, on to B now. What we need to do is produce the following. We want a non-retract rational torus. Okay. A smooth projective torque variety for that torus, satisfying some conditions. First, we're going to want to have a point for the torque variety. So we don't want a torus in the middle, we want a torus. We want to know a priori that the derived category has a full and tall exceptional collection. So already these two things here tell me that I'm going to have things that aren't even retract rational when I have a point that have full and tall exceptional collections. And then finally, I want a trivial torus. I want a torsor for my torus. That's, maybe I should put this in quotes because I'm maybe another lecture to explain what invisible means. I mean, I think you know what invisible means. It's a word in English, but precisely what it means. So I want some torsor that can't be detected by any Brouwer group. Okay. So given such an X, all I do is I just contract my torsor with that X. It basically cuts out the torus in the middle and glues in the torsor instead, and kills that rational point. Because it's invisible to any Brouwer group, when I take my exceptional collection and twist it, going from X to Y, none of it twists. It's still all a tall. No non-commutative stuff pops in. Okay? So let's see, what did I say? Okay, so maybe I can take a moment here since I have some time to so where do we get this X from? Okay, so we want a torus that's not retract rational. I've given you one such torus. All right, so we can take the norm 1 torus. For GM, I said we're going to do this over C, over Q. So this is going to be a biquadratic extension. And now, what I want is I want an interesting torque variety that compactifies this. So it's certainly not intuitive presenting it this way, but what you do is you think about this as living inside S3 cross Z mod 2Z. You stare at S3 cross Z mod 2Z for a bit, and you remember it's the automorphism group of the root system A3. Okay, right? S4. Okay. And then you remember, I have a very interesting torque variety associated to any root system. Right? So X over L will be X associated with A3, the torque variety associated with Weil chambers. Okay. Now I need to produce an exceptional collection on X itself. Fortunately, a useful collection was produced by Kastrovet and Tevelev for any X of AN. So they produce on any X of AN, they produce a Sn plus 1 cross 2Z stable full exceptional collection. Okay. That's sort of the first step. If you have something pulled back from the base field, it should be permuted as you move around via the Galois action, right? Okay, so then you check that this check it descends to in a tall collection on X itself. Okay. And basically, if I have a norm 1 torus, or the fact that this sits inside here also guarantees that, well, okay, sorry. I have to check if it descends to L for the action of this torus. I get a copy of the torus inside. We just said this torus is not retract rational, but now we have a tall exceptional collection. Okay? And now the only thing left is I need a non-trivial torsor for my Brouwer group, or for this torus, so that whenever I try and detect it, I try and send it into any kind of Brouwer group in some functorial way, it just dies. Okay? So I'm going to erase this exercise. Hopefully people will have answers by the time I'm done. So, in another paper we defined an invariant of an algebraic group that looks like the kernel over all natural transformations from torsors for the linear algebraic group. Into any Brouwer group. These things often arise as just connecting homomorphisms, where I have an extension where G is on one end and a quasi-trivial torus is on the other end, like GM. All right. So we define this, and then what we do is we compute it. I mean, we show how to compute this in a more manageable fashion. You compute this. Again, that's a bit of a, how much you've computed something is always in the eye of the beholder. It's not a number, so. And we check that, in particular, for this biquadratic extension, there is one non-trivial such torus that's invisible to all Brouwer groups. Okay? So then we just twist what we have here by that torsor, and then we get the example that comes in the statement of the theorem here in dimension 3. Okay? And then higher dimensions, you just cross with something, whatever you want to do. And in fact, whenever you have a biquadratic extension, you're going to get one of these. So they're just all over the place once I have biquadratic extensions. Okay. So I'll end with some questions. So does any smooth projective torque variety over a general field possess a full exceptional collection? This is known over C. Thanks to work with Kalamata. And remember, my definition of full exceptional collection means it can be division. So, for a general one, is there a full exceptional collection always? This question, by previous work with myself and Alex and Patrick, boils down to whether or not you have a full exceptional collection on your torque variety that is stable under the action of the automorphism group of the fan. And the way you usually make a full exceptional collection on torque variety is to choose some run of the Moy program. It's very hard to choose that in a stable way for the whole automorphism group. Okay. So we can often, and then come back to the question I asked before. So what is the mirror of this very Brouwer curve? It's a concrete way. More generally, what are the mirrors of torque varieties over canonical fields? I've seen a lot of mirrors of torque variety over C. Here you can inject some arithmetic questions into mirror symmetry in a setting that's not that far from what's being studied. So I think with that, call it good. Thank you.
Questions?
So in your proof of post theorem,
triviality of direction of this Picard group. The focus comes from this existence exception question, but is there some more conceptual way to see why derived category and rationality and
I mean, the nice thing about it's a tough question for me to answer because what I answer may not be satisfying to everyone. But for me, what I did explicitly write down, but what I've been trying to tell you is that torque varieties over non-closed fields are just almost linear algebra over the interviews. So once you know that, the structure of the derived category, at least the exceptional collection, things derived from it, should provide a very strong constraint on that linear algebra. So that for me, at least in this setting, is why it works. Of course, for more exotic things, you're not going to be as fortunate, but you can try and understand things by playing super, or at least try and pull out invariants.
Other questions? Thank Matt again. Okay, the bus is leaving at 4:45, so if you want to get on the bus, be there.
I don't remember if I told you.